Hello everyone, this is Ivan. I will introduce the topic implementing a virtual physical environment manipulation system based on ROS using Python and three.js. This was created from my previous company, Paya, focusing on educational system. We aim to university students to help them using a kind of tool, create, manipulate, and the train model in the virtual environment, which is synchronized physical one. It's really helpful to decrease the cost in the physical environment. And here we list all agendas we will talk about later. First of all, I will explain what is ROS and what is three.js, and then we will introduce digital twins concept, and also we provide a user interface to manipulate the digital twins systems. And also we provide a control panel to the physical robotic arm. And also we use three.js library and the byte framework integration in the virtual environment. And also we use a webrtc skill to connect the IP camera to display the physical environment in the virtual page. And then we use a connection to ROS cluster by ROS bridge, and it's written in Python language. Also, we subscribe it in the front-end side by ROS library, and also provide the ROS Cloud API to integrate the systems between physical and virtual environment. And also, in the end, we provide a conclusion for overall of the topic I will tell you later. My background is a little complex, not only focus on programming, but I am director as well. Already did some short films, and also I was volunteer some years ago working the Central America on an island near the Caribbean Sea, and also I like cycling. So yeah, I already cycled many parts of different countries. Yeah, so sometimes I use in this kind of stories to encourage my students, especially young generation, young engineers, to help them figure out what they really want in their future careers. Here are tools and skills we use in our project. First of all, is a design tool we use is Figma. It's a well-known tool most designers use it usually. And then we use some frameworks here. One is Byte and the other one is Vue framework. Yeah, we integrate both in our project. And also we use Vue router and Pinia to call our backend API. And also we use Tailwind and SAS to style our HTML pages. And also we choose some skills here. One is three.js to operate the 3D model of robotics arm in our virtual environment. Also, we use ROS bridge to receive and subscribe the messages from the robotic arm between physical and virtual environment. And also, we use webrtc to connect the IP camera to display the physical robotics arm in our virtual page. And also we provide the ROS Cloud API, yes, to update and record the status of robotic arm. And then we use some others tools like Docker and Jenkins for our continuous integration and deployment. Yeah, it's very helpful for quickly the implement deployment in our projects. It's very important skills. And then we can see the architecture here. The left part is the front end side. Yeah, we will talk about later. And the middle is the yeah DevOps, or we call CI/CD. Yeah, for integration and deployment. Then we see under the DevOps with the backend side, we use Python in combined with ROS bridge, and we also have local side in the right part. We use a physical robotic arm and IP camera to record the environment to show in our virtual pages. Okay, let's see the demonstration. In the left part, we see the robotic arm in the virtual environment and see how it works. And also in the middle part, we see there are many control gears here. And its button has information of the axis angles and the positions. So we can control each one access by each button. On the top right display, we saw the physical robotic arm in the IP cameras. You see it's synchronized in the virtual one there. And under the displays, there are some action scripts here recorded each steps. You control the gears in the middle, so you can record each action and repeat it many times. Beside the action scripts, we see some message here. Those messages to tell user about how the robots, how the system works well, or if it has errors, it will show some message here to alert the people now have some problem here. Okay, let's explain what is ROS and what is three.js. ROS, its full name is Robot Operating System. It's not really operating system. It must be installed on main operating system like Windows or Linux. So it's similar like a kind of framework to control and manipulate device of robots. Well, and also it provides some modular characteristics like stacks, packages, and nodes. So a node can contains many packages, and it's the basic unit of the robot operating system. And also, a stack can contains many packages as well, but a stack is more similar like a collection of packages. So, for example, when you use Anaconda in Python language, you use command to install Jupyter Notebook or TensorFlow. And after you execute the command line conda install, it will install not just one package, and many packages will be installed. It's a kind of stacks of those packages. So ROS provided this kind of function to help user can easily install their service and functions well. And also it's provide communication mechanism between ROS node. It must contain topic, service, action, libs. Topics is similar like a channel name, right? Each node can subscribe and listen the same topic, then they will get the message only by those nodes they have subscribed this topic. And also, it's provide a kind of service. So a service is a kind of function to provide ROS node to block current process to excuse others actions provided by action lib. So many actions lib they combined together to provide the different kind of actions for a service, and each action is non-blocking process will be executed in the background of operation system. Okay, so let's talk about three.js. Three.js is useful APIs and developed by the WebGL specification, and also it is collapsed and simplified well, so user can easily use it on their 3D environment from inside. So let's see the from inside. We use the Figma tool to design our mockup, right? So you can see how we design the mockups through Figma and artificial intelligence as well for generated automatically by prompt message. Like you see in the center of picture, we put a lot of keywords in the prompt box. After we execute the random button, we can see this kind of picture to help us design our mockup well, to design our main idea and the main color, main things, to design our main color well. It's really helpful to use generative artificial intelligence. After many steps of the kind of prompt messaging by generated AI, after many times execute the generated AI, you finally get this kind of markup with cyberpunk style. I list many keywords in the left side of this page. You can see here neon lamp, backgrounds are high contrast, and the metal and the cool color. Main styles in cyberpunk. It's a cyberpunk style markup. You see the whole markup here. So 3 parts of the user interface as well. You can see I already using box to separate the 3 parts. In the green box here, we see it's an information display. So it contains virtual 3D robotics on here, and physical IV camera here, and coordinated axis here, and the arrow message here. Inside the information display, it's have a small part of control panel here. You see the red box. The red box shows the reset button here, and the 6-axis angle control gear here. Okay, and the motor movement speed here. Okay, and the action recordings are editable here. Action recording here, and the last part of the sidebar in the orange box. In the orange box here, it shows logo and the device lister yeah, we can add the device or edit its name as well, and the user log in here. And yeah, we continue to show the physical robotic arm here. So here we see the physical robotic arm with its axis and the control. So you see many pictures here, different angle to see the physical robotic arm. Yeah, it's bigger ones, almost it's higher to half of adult bodies. So each axis to see each picture and overall has 6 axes in this robotic arm. The skill we use in virtual environment is three.js. So in the three.js fundamentals, we see there are some components here. One is scene. Scene is a virtual 3D stage where you can use cameras, objects, light resource, and all models we can present here. And the second one is camera. It's determine the position and perspective and projection of the display. The next one is objects. Yeah, like we see in the right side of pictures, the virtual robotics arm, we put this kind of objects in the virtual environment. So it contains many operations such as rotation, scaling, translations on one object like cubes, spheres, and models. And the next one is light. So light is the brightness and shadow effects of objects are determined by the position of light sources such as lights and direction lights and spotlight as well. So you can see the light pictures. We put the directional light on the top to brighten the robotics arm to make its models show the brightness and shadow effects on its model. And the last one is renderer. Renderer is to convert 3D objects and lighting information into 2 dimension. So yeah, actually we see all the 3D environments on website page is in 2 dimension. Ultimately, so we should convert all the 3D objects, include the lighting information, into 2 dimension, like transform the images on the screen by our camera perspective to the scene. So we will explain more details in later sliders. So let's see. First of all, we put a scene here in our virtual environment. It's empty in the scenes at the beginning. Okay, let's start to put the camera into scene. So in this case, we use perspective camera. It contains 4 parameters. First of all is field of view and aspect ratio and near and far clear plane. Here we see the pictures in the left side. There's a camera. Its direction to the right side. So its angle and the direction decide the field of view here. And how far the camera can see is decided by the 2 clear planes here. One is a near clear plane. The other one is a far clear plane. So only between the near clear plane and far clear planes objects here that we can see and displayed on our web page. Later, we will talk more details in later sliders. And how we decide each plan's size is by the aspect ratios here. So we decide aspect ratios by its width and height. Decide the size of the clear plan. So the linear clear plan and the far clear plan, its ratio is the same. And only between the two clear plans objects here that we can see on our screens later. Okay, so in the next I will explain is to describe the objects between the near clear plan and the far clear plans. So as I mentioned, between the two clear plans, all objects here that we can see only on the screen. So here that we see there are many blue cubes here. So only those blue cubes we can see on our display. And others like the purple cubes outside the two clear plans, we cannot see on our screen. So you can see it's very simple to create a cube into the scene by those functions here. The first one you use in the bus geometry to create a new geometry object and decide its mesh standard material by its color. Then we put the material and the geometry into the mesh object to create a cube object. Then we can use sim aid to put the cube into the scene. Okay, so let's continue to set a light into our scene. So you can see the pictures. We put a directional light on the top of those cubes. Like we mentioned in previous slide, we put a light on the top of our robotics arm. So the light can make those cubes looks well to obviously see its darkness and shadow. And so you see only it's the sense only the two clear plans objects we can make the effects of lightness on those objects. So out of the two clips, those purple objects cannot be affected by the light. Then we use the render function to display the scenes into the screen. Like you see, only the blue cubes here will display on the screens. And outside the clear plans, those purple cubes won't be rendered on the screens. So yeah, it's the render functions you will use in the final stage. Also, yeah, if we want to make the purple cubes into the scenes, we just backwards a little the near clear plans, measure one purple cube into the scope of the two clear plans. Like you see now purple cubes already in the front of those blue cubes and behind. Finally, you will see the purple is very close to the front of the camera. And behind the purple cubes, they are all blue cubes. So yeah, it's the perspective from the camera. And then we continue to see how we integrate a robotic arm in the virtual environment with the physical robotic arm here. We create a model contains six axes here, and on the buttons there's one base here. So it's very simple architecture, so we can easily to build up in the virtual environment and synchronize each axis to the physical one. Finally, you can see you can control the virtual robotic arms very easy to synchronize the physical one. Okay, so how we achieve the synchronization of virtual and the physical? So you see, we have some steps here in the left side. Then the right side, you see, it's a demonstration we see the before the CSS control and action execution. Then we combine it to change six actions angles. So those angles data will deliver to both virtual and physical robotic arms. Yeah, so you can see it's automatically synchronize virtual and physical at the same time. Okay, so it's based on the ROS robot operation system message format. So they are both in the ROS cluster, so they can easily to get this message. And we maintain those message and the data into the cloud by the ROS Cloud API. Let's continue to see the another skill webrtc we use for the IP camera information sent to the web page. So you see the webrtc buy the IP cameras by this hardware. We use a TP-Link table. It's cheaper and we easy to use in our country. So it's very simple. We using it by the RTSP protocol. It's a general protocol. Is by we set the user name and password and the IP address. It's a public IP address. Later I will tell you how we get the public IP address. Then so this kind of tool is open source and already someone create files. We can easily to start this service by the webrtc streamer, this GitHub project. It supports RTSP protocol and also can start HTTP server. You can easily to connect this server by another server as well, and compatible with Windows and Linux. And actually it's a Docker image, easy to use in a containerized. So you see, it's very simple to use. We don't need to modify too much, then we can use it well. Okay, let's see the program code of webrtc, how to use it in our project. So there are two IP addresses we need to set up. One is camera IP address. It's RTSP protocol to public for outside services, and the other one is RTC IP address. It's local address for our service to connect to the physical IP camera. When the components start up, we need a webrtc streamer to start a server in our local environments, and then we use the connect function to public the RTSP protocol to outside service. When we use webrtc, we encounter some issues here. Because a little different the usage of webrtc streamer in development and production. In development stage, we run the webrtc streamer locally, so we don't care about the public IP address. But in production, our main system, digital twins, and also the webrtc streamer API server, all deployed on cloud simultaneously. So we choose the Docker Compose to solve this issue to make them run at the same time. Then we still encounter a website appearing black during the development. So, finally, we found we must change UDP protocol to TCP protocol for our connection between the IP camera and the webrtc server. In the next stage, we master to public our IP address. So our IP camera without the external IP. So finally, we choose the port forwarding to solve this question. You can see we use a command socat. In Linux, we through the UDP. That's why we use UDP can work as well to inside service of our IP camera and webrtc servers to public from the outside computers through the public IP address. So it means other service can connect this webrtc service through the public IP address. Okay, let's continue to talk about the front-end side, another build framework to subscribe the ROS bridge to listen the ROS messages in the front-end side. Okay, so let's talk about how ROS cluster connect virtual and physical environment through ROS bridge library. So ROS library define a topic, each node, and then ROS node can deliver their message through the topic to each other. And so the front-end side using the subscribe function to subscribe this topic to get the message. And three.js components will change their angle and position depends on those messages delivered from the ROS cluster. So you can see we get a lot of message in the console log. So in the backend side of Python language, also we need subscribe to the topic in the ROS cluster. So we see how the backend side we subscribe it. We use create subscription here to the same topic, both the same on the front end side and the back end side. So the listener callback, we see when we get the message from the ROS cluster, we send those messages into the Cloud ROS API. We save all the information and data into cloud database, and also we send those information by different angles and position to the robotic arm. Later we will tell more details about how we use the Python language connected with the C# language to control the physical robotic arm. And so in the backend side of Python language, we also define ROS Cloud API. So first of all, is the category device. So user can use this device API to register a new device when they have a new device want to into the ROS cluster. Also, they can depend on their password and username to deliver the right certificate to the right device to make sure they can control or manipulate each ROS node in ROS cluster. So they can do some actions by the ROS API to synchronize the virtual and physical environment devices. So we continue to introduce ROS Cloud API. Here we show how we interact with get method of device API. It will respond JSON object to show the device IP name, brand, and other attributes. You see how we put JSON objects into our device agent API. The agent we define move, and then we put some data like angle, speed for each access. And we execute the API. The physical and the virtual robotic arm will follow those information to change the right angle and the speed. Here we see how Python code the ROS Cloud API. We use the function compared to angle lister to make sure the current angle they want to change is totally different than previous one. And if it's did, we will call the API instantly. So here, the second part, we see the device agent page function. We mentioned in previous slide. We put the agent move and put some data angle here to synchronize both on virtual and physical robotic arm at the same time. Here we get the ROS message from the Python WebSocket into the C# library to control the physical robotic arm. And we use C# SDK to encapsulate those functions to control the physical device. Like we can change each axis, and also we can set its angles and position, speed as well by those functions. In the end, we use DevOps skills, something tools like Jenkins and Docker containerize our applications to make them easy deploy. You see how we use Jenkins and Docker as a tool to deploy both on cloud and on premises at the same time well. So you see the script, we step by step to execute. And then after the image created, we put the image into the AWS ECR service. Then later we get the image from that to deploy on AWS environments. So all I want to present to you already is finished here. So let's give you a summary. So in this presentation, you get the basic concept of ROS and three.js as well, and also know how we integrate our system into virtual and physical environments, and know how we create a cloud-based interface to integrate the ROS Cloud API we defined and the local IP webcam. And also, how we deploy conveniently by the Docker and the Jenkins. Yeah, we Dockerize all application and make them easily to deploy by the Jenkins. So I hope you can get some knowledge from my presentation. So if you still have any question, just send me a message. Thank you.